Have a seat. Welcome to a beautiful Monday. It is apparently National Umbrella Day. I don't understand why you would put National Umbrella Day in February, but obviously they don't live in Iowa. Or maybe they're sun umbrellas. We're just noticing the sun was out, so maybe they're sun umbrellas. Either way, it is National Umbrella Day. We're going to do a warm-up problem today. We've got the 5-question multiple choice quick quiz to do, 15 minutes, 20 minutes max. And then we're going to start some notes for rotational kinematics. That work? Fantastic. All right, so let me get you the warm-up problem in a larger font so you can see it. I'll tell you the situation, then I'll let you discuss. So here it comes. In both cases, excuse me, a massless rod is supported by a fulcrum, and a 200 kilogram hanging mass is suspended from the left end of the rod by a cable. A downward force F keeps the rod at rest. The rod in case A is 50 centimeters long, and the rod in case B is 40 centimeters long. Each rod is marked in 10 centimeter intervals. The question says, will the magnitude of the vertical force F exerted on the rod be greater than, less than, or the same in both cases? Okay. So I'm going to give you just a moment to have a conversation, to think about this, to come up with an answer and, that reasoning stuff as well. And then we'll discuss. Sound good? All right. If you want to whiteboard it because that makes you happy, do it. To go. There we go. All right. What are you saying? Same, different, bigger, littler? So I see one person says the same. You don't have to write it. You can talk. You can use words too. Words are fine. Is that a consensus agreement on this whole table? You all think the same? Back table, we don't know. We're kind of shaking our heads. Elizabeth, what are you saying? A. You said A is greater than B. All right. Okay. All right. So we've got greater in case A. I know it's frozen. I'll get it unfrozen in a second. And we got the same. So those are the two things that we're arguing. Help me out, you guys. Talk me through it. Why do you say one or the other or something? Go.
So I think it's the same because so the rods are both massless, so that's that in your torque equation. So in A, the mass is 10 centimeters away, and the force is 30 centimeters, and it's the same thing for B.
Okay.
So yeah.
Okay, so you started saying something and then you kind of stopped the sentence. So take us with you on your train of thought here.
So they're basically identical things except for there's an extra 10 centimeters in A.
Okay, so you're saying we can get rid of this. Is everybody okay with getting rid of that? Okay, so your gut is telling you it should be the same, but you don't have physics to back it up. Okay. We'll go here and then here's that. Okay, she's just loud. Yeah, it's true. That's okay. You're next. Go. Okay. Normal force in B. Where do you want me to draw? Like here? Okay.
To make it on the same plane as the other two forces, you're going to like do FF perpendicular, which is going to be smaller. And
you want to do this? Is that what you're saying?
Yeah. And then that's going to have to be less than the FN of A. And then, yeah, because then FG plus FF has to equal FN. So if those two are both smaller. So if FN is smaller, then FF has to be smaller because FG is basically the same.
Is this FF here?
Yes. Sorry.
Okay, that's okay. I just want to make sure that we're all talking the same thing. And this is FG. And this is FG. Okay.
FG stays the same for both.
Okay, so this one is the same as this one. Do you guys agree with that? That FG is the same in both cases? Okay, I just want to make sure, like, when we start things, I want to make sure that everybody's in agreement because we don't want to fight about that later. Okay, So FGs are the same. We agree with that. We agree we don't need the pink. So keep talking.
And then, like, so the FN for A and B are the same, but FN perpendicular is smaller than FNA because it's like still.
Okay.
So this is the same as this. Like this and B is the same as this and A
Okay.
because it's.
So you're saying that this thing here and this thing here are the same.
Yeah.
Okay. I'm just drawing pictures.
So FGs are the same, but and they're both negative. For our FG and FF are both negative. So FG plus FF equal FN.
Okay, hold on. So F net here, you've got FG, you've got FN perpendicular and FF, and those have to add up to 0. So that's in the Y. Then you'd have to have an F net in the X, right? Which would be FN. I'm just trying to take what you're saying and run with it. That's what I'm asking. Well, and I see what you're saying, but I'm trying to jump off of what Elizabeth was saying, and she's making all of these like vertical.
Those are going up and down, which means that the only force that has next component is F, which means that it would be accelerating to the left.
Which means that I think there's got to be some sort of friction over here too.
Yeah, never mind.
Are you sure?
Yeah.
Okay. I'm not saying I don't think you're necessarily totally wrong. I just want to make sure. Hold on. We got to give Skylar a chance because he had his hand up next, and then we'll go to Spencer. Go, Skylar. Say that you do care about the angle? Is that what you're saying? Okay, so I'm going to erase this for just a second. Is that okay? So you're saying we do care about the angle? Okay. And what do we do about it if we care about it? What do you mean? Torque. What is torque? Force times distance, but is it any old force times any old distance? So if I've got a door that I'm going to open, I can increase my torque by, instead of pushing here, pushing there. But then there's also something about angles, right? So if I'm going to push with the same amount of force at the same spot, so I'm going to push here, do I get the same torque if I push like this as if I push like this with the same force? No? Yes? Talk to me, guys. No, you don't. So we need to take that into account, right? How do the force and distance have to compare? Distance from the equilibrium or the rotational axis. What's that? Right. So if I've tried to draw these equal, but I didn't really. So if that and this are the same length, the torque is going to be just this part of the force versus that longer one. You agree? So that means that it's force times distance, where the force and the distance need to be what? So here's my distance. Proportional. Not proportional. They have to be related somehow. Why did I pick the blue part here? Yeah. They have to be perpendicular. The force and distance that we're talking about have to be perpendicular. Okay. So the angle does matter, doesn't it? That's what Skylar was saying, and that's exactly right. The angle does matter. So what am I going to do with that information? Does that answer my question? Okay.
And then have some y component and an x component for FF, and FM.
Okay. What's that?
Technically closer to the like in X direction, it would be closer if it was.
Oh, so you set like the rod,
variable.
that's the axis. Like
Say again?
it's like when we did like free body diagrams on a ramp, like
Mhm.
you set that to be like the
Mm-hmm.
perpendicular parallel axis, and that becomes like at an angle. You have
Yeah.
to like draw the components.
Does that make sense? So the part of the force that you want for FG is just this part here. And the part of the force that you want here is just this part here. To the thing that's like the thing that's rotating. Yes. So our distance here is 10 centimeters. Our distance here is 30 centimeters. This thing has to be perpendicular, and this one has to be perpendicular as well. Okay, but that doesn't answer our question yet. I don't know. Are they the same or are they different? They're different and A is greater. Why?
So, but,
On A or on the left side of B?
they're both 200.
Okay.
But since B is at an angle, the perpendicular angle, it's the component of that 200.
Whatever. Sure.
A little bit less.
Okay.
And then we're connecting so on that side of the so that
This one here, the green one.
yes. Although we're trying to.
But I'm not comparing the green one here to the brown or to the black one up there. What does the torque have to equal in each system? Right? The torque has to equal 0 in both situations. So on A, the torque for A is going to be Fg times 10 plus Ff times 30. Does that make sense? So that means that Fg has to be, what is that going to be? 3 times bigger than Ff. Fg equals 3 FFs. That makes sense? Check me, because I sometimes make silly, goofy mistakes here. The torque for B is Fg perpendicular times 10 plus Ff perpendicular times 30. How does Fg perpendicular compare to Ff perpendicular? 3 times Ff perpendicular? These green ones here, they are parallel to each other because they're both perpendicular to the rod. But Fg perpendicular has to be 3 times Ff perpendicular, yeah? How does Fg here compare to Fg here? They're the same, right? So anything that this is going to be, so if we write this out, so Fg perpendicular if I use this angle here and this angle here, Fg perpendicular is what? Fg times the cosine of theta. And Ff perpendicular is Ff cosine theta. So if Fg perpendicular is 3 times Ff perpendicular, how do Fg and Ff compare in this thing? What's that? Yeah. So FG has to equal 3 times FF, right? Do you guys follow what Spencer just said? And if that's the same, if that's the case, and if this is the case, how does FF in B compare to FF in A? They are the same. If they weren't massless, it would change. Well, yes, but then you'd have to have another force in here. And then it would, yeah, it'd be harder. Yeah. Do you remember how when we were doing that bridge problem, the problem before, I said that the mathy stuff is not stuff that we'll do an AP, like on the AP test, right? There's not any mathy stuff here. Are you with me? But there's a lot of thinking here. This is a hard problem, but this is the kind of thinking that they ask you to do. Does that make sense? So seeing those ratios and seeing those relationships is what they're going for. Way more so than plug and chug. Okay. Yeah. Right. Because you're pushing, because you're trying to get it to not be in equilibrium. You're trying to get it to actually accelerate. Does that make sense? Okay. So it's a little different in this case. Yeah. Yeah. Good question. Questions about this? So are they the same? They are the same. The forces are the same. Yes.
So wait, does that change the force changes all because of the angle? How does the force change the mass?
So the force that is causing this torque here is different on this one than it is on this one. The magnitude of this green arrow and the magnitude of this black arrow over here are different. But this black arrow here and this black arrow here have the same magnitude. Does that make sense?
Does that magnitude of the force into the FG change because of the angle?
The orange forces here do not change. They're exactly the same. But this green arrow, so the component of the FG force that's causing a torque here is different than it is over here.
So the torques in the two are different,
but the net torques are zero in both cases.
Okay. But then the actual, like, just the forces that are being applied are the same.
The same.
It's the like distance, like the horizontal distance to the rotational axis.
Correct.
Okay.
Yes.
So the distance is changing, the force is not.
You can look at it either way.
Okay.
So you can either draw the triangle like this and leave that force acting on a shorter distance, or the way I did it was that you use this length and then the force changes, the force causing the torque.
Okay.
Either way, it's still a ratio, same ratio. Yeah. That's okay. So not to confuse our friends at home, I just want, oh, it is, thank you. You could do this and then go like this. Right. Yes. Yes. Does that help a little bit? Okay. All right. Now, if I haven't completely confused you, we're going to move on. You do your quiz. 5 questions, multiple choice. So the question on the board says, I don't know what the ding was, but what is it, me? I don't know why it's starting to ding. All right. The question says, a rotating carousel has one child sitting on a horse near the outer edge and another child sitting on a lion halfway out from the center. Question is, who's going faster? Give us a start. Go ahead and give us a start chance. They're going the same speed. So I hear somebody, I'm just going to write this down. Same. I know that that's frozen. I'll get it unfrozen here in just a sec. I hear the same. I hear the horse. The horse child. The child on the horse. I mean, yeah, I guess. Yeah. Okay, you want to give me some reasoning? I need some.
Okay, so
physics needs to have
the
reasons,
horse
right?
is further out. it travels, it goes farther, right? But they do a rotation in the same amount of time on like a fixed thing. So because the arc length is longer, but they do the same, like they do a rotation the same amount of time, this speed has to be faster.
Okay, so you're saying the horse because the arc length, you said? The arc length, say it again, arc length what? Okay, whatever, yeah. Okay. Now, who wins? Who wins the race? Well, if no one wins the race, then how is somebody going faster? But then they have to win, right? If you're going farther. Okay, but if you're telling me that the horse is going faster, then you must get there first.
Okay, but the circle, it's a bigger circumference. So it's like, if you cut the circle and then stretch it out,
Yeah.
it'd be longer.
So you're telling me the horse is going to win?
Yeah, but no.
Well, no, but because they're both pivoting around the same place, so they're always like.
Okay.
Yeah.
But do like I can do that.
Okay, so they're traveling a different distance, same amount of time. Like if they have.
So that means the horse wins.
What's your definition of win?
So it depends where you draw the finish line. So if the finish line is like a radius of the circle, none of them will ever win. But if it's like this,
then the line will never get there.
Yeah.
Then the horse will win
if it's like
twice.
this, then the line will win. Like if the finish line doesn't come from the radius.
Oh. So what you're telling me is what Caden had asked a minute ago, and I kind of ignored him because I wanted to screw with your heads a little bit because that's my job, right? So the whole thing is that it depends on how you're measuring things, right? That's what it's all about today, okay? That's what it's all about tomorrow. That's what we're doing right now. There's a gold piece of paper in front of you, okay? That gold piece of paper in front of you is us relating everything we already know to everything we don't know yet, okay? So there are two kind of big columns. So there's like the quantity stuff over on the far left. And then the next thing over is it's labeled translational. So translational is all the motion that we've studied for the last however many months we've been together since August. We understand translational motion really well. You know about displacement, acceleration, you know about kinetic energy, you know all that stuff about translational motion. But now in unit 7, all in one unit, so we did 6 units already, right? 6 units of this happy-go-lucky translational motion stuff. And now in one unit, in unit 7, we're going to put all of rotational motion. Okay, we started already, but we haven't gotten there. We haven't gotten very far. And this is where we're going to kind of organize ourselves about. Okay, so let's start with the stuff we know. You know what displacement is, right? What letter do we use to mark displacement usually? X or delta X maybe, depending, right? Like, so position is X, and so displacement is change in position. What units do we use to measure? Not feet, not nanocentimeters. Base unit is the meter, right? What's the definition of velocity, guys? Don't overthink it. Yeah, don't overthink it. Delta X over T, change of position over time, right? Units for velocity, translational velocity, what are the units? Yeah. And acceleration, we defined that one as well. This was like August. Yeah. Units are? Good for us. Okay, so that was August. Now we're here in February. We're doing the same stuff, but instead of talking about translation, so translation means in a straight line, right? Rotational means in a circle. Instead of measuring things in meters or in nanocentimeters or whatever, okay, now we're going around in a circle. How are we going to measure a displacement in rotation? We're going to use radians. We are not using degrees. Even if you like, I heart degrees, like whatever, we're going to use radians. And it's important. Nope, we just write RAD. Rad. And the funny thing about radians, and I'm glad you asked, is that radians, it's just a ratio. You guys know this from math. We're going to go over it again tomorrow, okay? But we're not going to spend a lot of time on it right now because we don't have a lot of time to spend on it. But I just want you to know that it's just a ratio. There's really no big deal, okay? Theta is generally measured as an angle counterclockwise, okay, from the x-axis. Okay. Easy peasy, we got this. And again, we'll go through that a little bit more tomorrow. I want to get all these pounded out here though. Just like velocity, translational velocity is change in position over time. Same here. It's the change in theta over time. That's all it is. No big deal. Delta theta over t. Okay. This thing is known as angular velocity. Rotational velocity. It can also be known as, and this one's a little bit funny, again, we'll go over this tomorrow, but I want to make sure I have it written down, angular frequency. You've met this one before when we talked about it as angular frequency. What is it? It is omega. Good memory. Omega. And the units are radians per second. If you remember that radians aren't really anything, then this is just 1 over seconds, which is first, which is why we call it angular frequency. Yeah. And then we can take it one step further, right? We can say that just like acceleration is change in translational velocity divided by time, we've got a similar thing here that's going to be the change in omega divided by time. Okay. This is our angular acceleration. And the thing, nope, it's not though. That's the thing, it's different. It's different. We'll get there soon, but we're not there yet. Angular acceleration is just speeding up or slowing down as you're going in a circle, which is different than centrifugal acceleration. Okay? You're going to notice a trend with rotation, and that is that we're using Greek letters for all of them. Angular acceleration is going to be marked with the letter alpha. You got it. And the units for it, my friends? The units are? You got it. This. Okay. We're going to stop right there. If you have a whiteboard out, if you'd put it away, that'd be great. If you wouldn't mind putting up some chairs, I would very much appreciate it. The bell's going to ring, I don't know, in about 40 seconds or so. But it's not. It's alpha. It's different. And if you start calling it, it's really crabby at you.